point does playing become a serious scientific activity rather than a pedagogic trick?
Yeah. This happens when you take the intuition and the strategies that come out of that, and then you start using those for new research or new solutions, right? If you take DeepMind as an example again, setting out to solve intelligence, and they used games as the platform to develop that, to do it. And so being able to solve, like I said, and play games requires intelligence. That's the premise. And then being able to play games, or in my case, being able to play quantum games, means you have quantum intuition, quantum intelligence. Apparently, you can reason about quantum systems in a way that allows you to make predictions of them and to develop strategies for them. And I think that's an essential component that you need as a researcher, for example, to solve scientific problems, right? To have that base understanding, the intuition, and then you can build on that. Imagine that you don't know how to do basic math. There's no way in which you can do quantum research, right? Somehow you have an intuition for basic math, right? Or for gravity. And without an intuition for gravity, it's going to be very difficult to be an engineer, right? And build things. So I think that's an essential thing. And the example, for example, I wanted to give that I just mentioned, we know, this is on the research side, if you make a random quantum circuit, it's useless. You can prove this. On average, all circuits that you make have non-interesting expectation values. They do nothing. We can prove this. It's a mathematical, straightforward kind of thing. Well, straightforward. It's a mathematical thing. You can prove that most circuits, almost all circuits, are not interesting. So this includes, a circuit. All the quantum computations we do are circuits. Shor's algorithm, Grover's algorithm, they're all circuits. Shor and Grover are exceptions. They are interesting circuits. Grover's algorithm has a parameter somewhere, particular rotation angle, and if you move that rotation angle by 1/10 of a degree, the entire circuit becomes useless. It has to be exactly that point, exactly that angle, right? So this is a very difficult thing to find in an unstructured way. So these interesting circuits, we call them peaked quantum circuits. They have an output on some interesting value instead of an average of 0. And we don't know how to make peaked circuits. I cannot give you a recipe or a protocol that says, or give you a circuit, or you give me one, and I look at it and I say, this is, at least it, I'm not sure what exactly it does, but at least it is peaked. At least it gives you some non-zero outcome. We don't have that. But, if you can make a computer try and calculate it, if it's a few qubits, or if you have many qubits, you need the quantum computer for this. But so this bugs me. I think there must be some structure in this, right? Now imagine how do I find that structure? For me, I would make it a game. I would say, start with 1 qubit, and I give you the challenge. Now, make this circuit output this, right? So now I give you 3 qubits. You build up slowly from smaller circuits to larger ones. And I am convinced that at some point you start recognizing combinations of gates or operations that give you interesting outputs, right? You build these gadgets, as we call them, for example. And so you build an intuition for looking at parts of circuits or combinations of gates that do interesting things. You abstract them away. And at some point you learn how to make circuits that get closer and closer to these peaked ones. This is a thing that as a researcher makes sense, yet I would never imagine sitting down and just literally trying all these combinations, right? If I turn this into an interactive thing with a game, then somehow it's a very natural thing to do, to me at least, right? Especially if it's a web app and I add scores and I make, a nice interface, and then anyone else can also start playing around with this, right? It doesn't have to be a researcher, because now it's a game. You don't need to, if I abstract away the underlying quantum. And so this is another example next to quantum error correction where I think in the building of peaked circuits, using collective knowledge of all the smart people who are out there, and at the same time building them as a workforce in quantum is an excellent idea. I think I'm biased.
I think it's fascinating, and I can also see that it could really help bring forward the space. Maybe as a follow-up, how will it contribute to new quantum mathematics or new algorithms?
Yeah, I think this really resonates with the answer I just gave, right? So this finding new algorithms, a large part of that is being able to come up with circuits that are peaked, because they at least do something interesting, right? Now, if you have an idea of what those circuits, then you can ask, what do those circuits do, right? Starting from the smaller ones, finding those combinations of circuits or gates that do interesting things. You can start maybe finding ways of puzzling them together. This is also a non-trivial task, because it's quantum. The logic doesn't just sum up or add easily, but having algorithm, if it's an interesting algorithm, is not an average zero circuit. This is very clear, because then it's not useful. And so I think that's the answer. Finding ways of making interesting circuits will directly help understand what algorithms we can make.
And are you positive about that? So for what I find fascinating is that the CEO of NVIDIA, Jensen, he says, okay, if the cost of compute go down and if compute is stable, in the mix shift from CPU to GPU, in 2024 there was some saying, okay, all intensive workloads will migrate from CPU to GPU. And then the pushback he got is, yes, but CPU will not disappear. And there's already software written for it and algorithms written for it. And those algorithms are non-existent in GPU.
Yeah.
And his feedback is, if you have the lowest cost of compute and if the compute is stable, then smart researchers and developers will create new algorithms for GPU. But how do you see this for quantum? Are you optimistic about this, or were you looking for that it would increase your conviction?
There's so many things going through my mind now for this question. I mean, if cost goes down, at least I can tell you probably that I'm not convinced by that argument, because I imagine that there are cheaper things, alternatives, or better alternatives to silicon in many ways. I don't see, there's no chance that we will move away from silicon and easily, right? Even if, it becomes cheaper to do something else. Everything is so set, all the supply lines, everything is, so that it's not just changing this thing. It requires changing the entire flow of all kinds of resources. I think the same is true for CPUs and GPUs. GPUs, of course, are started out as very specialized devices for doing linear algebra, basically, for doing, right? Now, I will use that as a bridge to the quantum case, because quantum processing units, QPUs, if you will, and quantum computing, and I am offending a few people by saying what I'm about to say, but quantum computing is also linear algebra with complex numbers. You need a little bit more. But I think if you will, you can understand almost all of quantum computing if you know linear algebra and complex numbers. So GPUs, in a way, are already well suited for simulating quantum systems. They don't deal well with complex numbers, but they have the specialized matrix vector multiplication things. Now, I hope I'm wrong, but this is again the thing of not being able to predict the future. But I don't see a future in which quantum processing units will replace GPUs or CPUs. In a way, if you will, now that I'm saying this, QPUs do linear algebra with complex numbers. So maybe they could replace GPUs. I don't know. But there's so many things that people typically sweep under the rug that need to be sorted before I can see any of this happening. QPUs, again, depending on the hardware, but almost all of it has to be cooled to very low temperatures. You need a lot of infrastructure also for having all the cooling around, for doing the isolation from vibrations. It's not so easy to just take, and replace them. And also, they're extremely slow. Quantum computers this is a big misconception. They're not fast. I can tell you much more about this if you want, but they can do certain problems. They scale better. But the laptop that I'm on now, does operations in femtoseconds. It's extremely fast, the gate times. And those quantum computers, including all the, the readout of the classical data, take milliseconds, right? There's a million, an order of magnitude in between. So for my quantum computer to do that classical thing faster, even if it would at some point do faster, simply using my laptop for the same problem now, it has this advantage of being 1 billion times faster already, simply because the quantum hardware is so slow. So only if my problem is so large, 1 billion times larger, that it would take my classical computer to perform, at this point, with this current hardware, of course, hardware will become faster, etc. It would still not make sense. It would still not make sense to use the quantum computer, even though you can prove at some point it will be faster. And this is a hard reality, because in the real world, we don't have energy networks with 1 billion nodes, right? We have 1,000 maybe. I don't know how large the energy networks in the Netherlands are, how many nodes, but I would not estimate them to be, not 1 billion. Right, so there's all kinds of hardware advances that are needed, more things that are needed. And so at least for the near future, I don't see QPUs taking over any of the classical compute.
But one of the things that I find fascinating, if new algorithms and new mathematics will come, then it could increase the probabilities that QPUs play a more meaningful role. Assuming that they scale. My best guess is that around 2030, that they scale to 100 logical qubits, and around 2030 that you reach 1,000, 2,000 logical qubits. And at that point, you can start to do meaningful things for that. But then still, it would be very helpful if new algorithms or new math would be discovered. But
for sure.
How do you track that? How do you track or how do you analyze if the ecosystem is probabilities for the discovery of a new algorithm are going up?
If I could predict this, right, then I would be rich already. This is I've been in the field for a long time, and there was a time where you could sort of linearly predict the growth. You could see, every year something was better and easier, but that has gone out of the window. There's so many investments, and I'm surprised continuously that there is a paper that achieves something on the roadmap that was not predicted to happen in another 3, 4, 5 years. Yes, they are sort of constrained, like it only works for this particular case and not in general, but they happen more and more often. And so being able to predict these things is very difficult. In fact, I think yesterday there was a paper on the archive, a preprint, that makes I have not looked at it in detail, but the claim is that they can now factor the RSA 2048 with 100,000 qubits. And, the numbers for this, like in 2020, were, I think, 1 billion qubits, right? And so... don't pin me down on this number. I can find the exact numbers, but it went down very rapidly. I think 1 million or so was the last, and now another order of magnitude was taken off, right? 100,000. And so now, you said 2035, we have 2,000 qubits. We have logical qubits, right? So then you have already the order of 20,000, if not more, 200,000, physical qubits. Depending on the code and all, etc. So, I would not be surprised if in 5 years we indeed are able to crack RSA 2048, right? If you asked me 5 years ago, I would have said 2050, right? And now suddenly 2030, it does not seem that outrageous.
But Evert, on the software side. Could you walk the listeners through the ecosystem? So if you want to study the ecosystem, where can you find the amount of developers or the amount of people who are working on quantum software? And is it growing very rapidly? How does it scale? You mentioned in the Netherlands with a unique choice.
The quantum software in the Netherlands, we have Leiden. We have an applied quantum algorithms group that I'm part of. We do a lot of quantum software. Let's go for the academic side first. And there's QSoft, which is the institute in Amsterdam, who do quantum software. I think at least here, sort of in the Randstad. There's also some people doing this in Delft, of course, but Delft also profiles themselves on the hardware side. Really, Leiden, Amsterdam is where you find the research on the software, quantum algorithms, quantum machine learning, all of these types of things are represented here. It was just launched. We are a partner of this as the AQUA, the Applied Quantum Algorithms Group. Also QSoft is in it. The Quantum Software Alliance, I think it launched 2 days ago. This is a global alliance of all researchers and companies, or not all of them, but many, making the point that we should be investing more in software. A lot of the investments now go into use case development, immediate value things. Less and less is going into the fundamental research. And I would want to argue that finding new algorithms, the new mathematical structures that you mentioned, is a fundamental research question. It's not driven by taking known algorithms. We have a quantum algorithm zoo.org where you can find for classical algorithms if there is a quantum speedup in a quantum version, right? This is a viable path. I could go and talk to biopharmaceutical companies, find out which classical algorithms they use. And for each of the classical ones, I can tell them, hey, you should swap this one out for the quantum version, right? Because it will be faster. These are the use case development, use case searches kind of things. But really finding those new algorithms, those surprising ones that with 1,000 logical qubits, it turns out you can do something useful, right? That really is the software side of things. And I think there's not enough. I wish I could point you to the right place immediately.
Yeah.
I'm not sure it's there yet, right? That's the thing.
But I think if you are an investor, how would you study that? Is it, for example, the amount of people going to university? Is it the amount of people using certain software tools? Is it maybe the amount of people that play quantum games?
So the latter one for sure, because this is the whole thing about doing the creative, finding that meaningful thing, interesting thing you can do with 100 qubits, right? That's simply, I think you have a good chance of finding something you cannot predict in this gamification manner. So that's one. Look at these, the manifest and the things that go into the Quantum Software Alliance. And there's also associated papers with the things that need to be done. There's not many. Track startups in this direction, right? The companies that look at specifically at quantum software ideas. This is not the same as, companies that do AI for making better software, like quantum software. You have companies that are very large companies that use AI to optimize algorithms, but they optimize parameters of the algorithms or of the hardware. It's a different thing. They're not developing the new algorithms. And there's also companies that classically simulate quantum systems. These are called quantum-inspired methods. Also not the same thing, right? They use tensor networks or other techniques to simulate quantum systems. Super relevant, super interesting, because a few times it has happened that people claimed, quantum advantage, doing something faster, and then some clever tensor network people showed that they can achieve the same thing with tensor networks. So that's great. I mean, if nothing, in the worst case scenario and nothing else comes out of quantum, then at least quantum has been a tremendous driving force in making better classical algorithms. We are quite convinced that that's not the right, that there is something meaningful in quantum. So I just want to make sure that's said explicitly. But yeah, track people going into the quantum workforce in the universities, especially in the more fundamental universities, right? The ones that the master tracks. There's master tracks that are aimed at quantum information science and technology. We have one between Leiden and Delft, for example. And, more people going in that also means more people going into quantum software. Also hardware, but also software.
Evert, can you maybe globally make a rough prediction? How fast is it growing? Is it doubling? Is it increasing 20%? Or is it flattish the last 5 years?
So I've looked at some of, I do look at some of the, larger reports, the McKinsey and Boston Consulting. The immediate reaction I have, and also my quantum expert colleagues have, is that it is quite overblown, the promises that they make, simply because it typically doesn't take into account all of the things under the rug. But researchers also tend to underestimate things. So the truth is somewhere in the middle. And I think, if I remember correctly, things they predict is around 35% of growth in all of these quantum sectors, with one of the main limitations being workforce. We really need more people. So I think one of the things to track really would be people, would be the workforce. And I notice at the university, if I want to find a good postdoc, it has become much harder because there is not enough people. And so industry pays much more. They want these people. They can pay more. I'm at university, I cannot. Again, if I make the quantum DeepMind, then I can also offer them competitive salaries. That's another reason. But I'm just saying, I clearly also notice that it is harder and harder to find good people, and they go to industry because they can pay more. And so this bottleneck of finding good people is real. That needs to be solved. We need to make, workforce, which again, we do with games, right? We start with the younger generation, have them play tic-tac-toe, and then by the time, they enter the workforce, they are native in quantum. They have the intuition.
Okay, now clear. Thank you, Evert. I want to switch topic a little bit on quantum machine learning use cases.
Yeah.
You did a lot of work on that. When you evaluate claimed use cases, what are the first two questions that you ask to test the credibility?
Excellent question. I ask, is this problem truly a hard problem for classical computers, right? It must be true that this is really a problem I could not have done with my classical computer, right? And then maybe not like right now, because like I said, I think almost all of these things I can do on my laptop right now. So it really has to be the structure of the problem. If I make the problem larger and larger, does it become harder and harder does it become harder faster for a classical computer than for the quantum case? It has to have that property. Otherwise, it will never be relevant. And I also ask, did they do this feasibility study? Did they actually run it on hardware? Did they take into account all of the issues that come with that? Because yes, Grover's algorithm gives you a quadratic speed up for doing an unstructured search. But you will find that if you actually try to do that on hardware, you also have a quadratic slowdown somewhere else in either the uploading or the readout, right? Yeah. So for real world data problems, it's going to be this is a critical thing to evaluate, right? Do you actually get the speed up if you take the whole thing into account? Which incidentally means if this is a claim for speed up or like a quantum machine learning case where the input is quantum, so you do that on the quantum simulation directly, I think then you're already in the green for this, because then you don't have to have this uploading and readout thing. But yeah, is it truly a hard problem? And did they realistically take into account all the other things that need to be covered? Those are the first two questions I have.
Okay, thank you. Which categories of use cases have quietly slowed down and which categories strengthened over time?
Yeah, so the things that come to mind for me are the variational quantum eigensolvers, which people at some point thought these are interesting things to use for quantum chemistry. It is a subset of quantum machine learning. Quantum machine learning is this fascinating thing where, like I said, for many real-world problems, it is not clear and it's tipping a little bit into the direction of really not sure how and where it's useful. But at the same time, we have so much evidence that says there has to be a thing where it is useful, right? We're looking for that. So this is on the one hand, going down, but also, more and more interesting because it's such a challenging problem. Logistics and optimization, to me at least, when I see use cases and from the sentiment I'm getting, is becoming that sort of quietly weakening, I would say. So this is because of those things I mentioned before, like that for optimizing networks of 1,000 nodes, we have such good and fast classical algorithms. It's not clear if you get that speed up overall. So this sort of optimization logistics is less. This is my perception. I know some people will think differently. So that's one. What has strengthened and is clearly strengthening still is really the application to intrinsically quantum problems, like simulating molecules, making new materials, because ultimately they are quantum systems, right? So applying it to chemistry and physics problems for better solar panels, better energy, better batteries, they are gaining in traction.
And where do you base that evidence on?
So this, basing on it is papers, is like research, right? Is research, because that's the thing I know how to evaluate most easily, right? But also a little bit in terms of, I do keep track of companies and investments, right? And some companies I wonder, like, why is this a company? How does this exist, right? But I think the strongest evidence really ultimately is, it's fun if someone wants to say, I can do better logistics with quantum computers. But if at the same time we have a hard proof that it will not work, it will not scale, then I would trust the proof, right, in this case. There are cases, and I should say this out loud, where this is not true, because if classical computers only did the things we knew how to prove, we would not have had AI, right? I mean, AI works empirically, and there are many things we don't understand about them. So it's also a matter of taking this risk. But yes, papers. It's just use cases on the optimization and logistics. I don't see them really doing things that I'm convinced by you could not do with classical computers better, at least in the next 5-10 years. And given my background in condensed matter physics, before quantum computers were a thing, there were already simulators of materials that trapped ion people. They were doing this in the cold atoms. They were doing this for a long time. They were simulating the Hamiltonians of quantum systems, trying to find how do superconductors become superconducting, right? And for some reason, people didn't think of them as quantum computers because you could not use them for generic computations, but they are already excellent at simulating specific quantum systems. And so those types of quantum computers are worth it to me. And they are, people are now realizing in the literature also that it makes sense to call those quantum computers, they're just specialized quantum computers.
Okay, fair enough. Can we talk a little bit about the implications for quantum computing and verification? As quantum computers scale, do you think machine learning-based diagnostic will become unavoidable?
For now, I think yes. Somehow I have trouble imagining in 30 years, let's say when we have, in that scenario, stable working quantum computers, I would somehow be surprised if they rely on black box tuning and optimization methods, right? Yeah. That would be weird to me because you want to trust them in one way or another. I think it's also, so I imagine that at some point we understand these systems better, or we understand what the AI is doing and we turn them into hard-coded or heuristic algorithms. But until that point, I think we need all the hands we can get, and AI is extremely helpful in this. It's no longer feasible as a human in the experiments or in the lab to tune 60 knobs at the same time, right? And they all influence each other. And figuring out what the right settings are is I think we really do need AI for this. But I do think, and I do hope that at some point we can ask that AI, or it becomes clear, we can interpret it and understand why it's doing these things. And then we say, okay, so actually it means that this is the right heuristic, we should do that, right? And then the AI can be used for other things. Yeah.
Can we meaningfully claim quantum advantage if verification itself becomes opaque?
Yes, if we can check the answers, right? So for some of the, hard problems, it's hard to compute the answer, but once you have the answer, you can verify. You can just stick in the answer and see if it's correct, right? So if you give me this quantum computer and I ask it, solve this problem, and it gives me an answer, and I can verify that the answer is correct, then I think you have a black box, if you will, or a quantum computer that gives you an advantage, right? If that computer does it faster, better, memory, or like more efficient than the classical one. But you can also, so the verification of quantum devices is a huge research field, right? You can use other quantum devices to verify quantum devices, quantum verification. I am not the expert in this direction, but I do know some of my colleagues are, and I know that there's a lot of smart people thinking about how to do verification of quantum devices. And so I'm not worried about this. I think, yes, there are ways to claim quantum advantage if the verification of the answer becomes difficult and using other quantum devices.
A last question on the machine learning use cases.
Yeah.
Do you see a future where machine learning plays a similar role to error correction? Not fixing errors, but detecting regimes of failure?
Yeah, so so if we have those heuristics or those better hard-coded algorithms for fixing the errors, that's what we were just discussing. And then you have a higher level of like the meta level, right? And just maintaining, operating the quantum hardware, things that also the humans would be doing now. And so I see a role for this, right? Also scheduling of the jobs and routing, turning the circuits into useful, mapping them onto the quantum hardware. I think there are definitely places where AIs and machine learning can help operate quantum computers.
Who do you see, Evert, as the game changers in the quantum technology? If they received X amount of money, they would really unlock the main obstacles.
What I would want to, I've never done this, but what I would want to understand is, why did transistors win the race? Classical, right? They're also based on quantum effects, but we have different modalities in quantum hardware. You mentioned some of them, the ions and the spin qubits, and we have the photons, or the Majorana ones, the topological ones. It's so hard to make a choice and to predict which one will be the right one. So I think the question you're asking on the hardware side is this question, is which of those modalities should we start pick? We should just say we are going to focus on spin qubits. They're not the easiest to work with, but we have the whole silicon industry, right? That will solve many of the problems that come after, right? Or we say, let's go for photons because they can work at higher temperatures. They don't have the noise issues because they don't interact, but it's extremely hard to make two photons do something and talk to each other. So all of them have their particular engineering challenges. I'm sure you're well aware of that.
But are there specific persons that you feel that from the area where you look at, that you say, if those people got capital, I believe they can solve an important problem in the ecosystem that will bring quantum forward? Who would that be?
Well, I think of the people I can judge best in these directions are, of course, the people in the field and my colleagues. So, for example, my colleague here, Vedan Dunko, he is really an expert on all things quantum machine learning and proving which problems can meaningfully be done on quantum computers. I think I would talk to him often, and I'm continuously surprised by his depth of knowledge on these things. I think if he decided, let's make a company on these things, if he wanted to do the DeepMind company with me, then I think that should be.
Okay, that's interesting. Can you give a 2-minute pitch to wrap it up, where you explain the gamification of quantum technology?
Yeah.
Why should investors and policymakers, why should they care?
Yeah, well, I think the most important thing is they should care because it's one of the things that gives you much more immediate value. We've been saying, quantum computing and fault tolerance is decades away, but the bottleneck is not just the qubits, I think, like making more of them and making them more stable. It's also the workforce, especially the workforce. I think people mentioned this, I mentioned this before. It's one of the bottlenecks that limits growth. And I don't want to wait for perfect hardware. I don't want perfect qubits. I want perfectly managed noisy qubits. And I think we can only get value out of them by turning it into this strategic playground, this gamified route where people without quantum background, but the hackers and the tinkerers and the creatives who come up with cool and crazy new ideas that make me go, like I said, like, hey, I didn't know this was possible. This is cool, right? I want to enable those people, right? And I think if I enable those people, we will get value out of finding unexpected new algorithms that can run and that can do useful things with noisy qubits. So that not only helps, giving them those native tools and going to the big AAA studios and have them incorporate something quantum, either in their narrative, where I can guide them, or in generating textures that have a different feel than the classical ones, or in random numbers. But it also helps build intuition for broader audiences with games, which helps building the workforce. And we should invest in them now, even in the younger generations, getting them excited for quantum technology. We will need quantum programmers, and we have to start giving them this intuition early, because you don't find it in real world quantum intuition, unlike gravity. The games are benchmarks. No, I didn't even mention this, but no current hardware provider can run tic-tac-toe real time, right? It's a super simple game, but no one can do that. And now imagine that IBM says, hey, we can run one round of tic-tac-toe coherently, right? And then IQM says, we can actually run 3 of them, right? Then you get this sort of race that helps drive the hardware. And the final pillar I want to mention is that it's excellent. This is, for my background, for research, right? This is the DeepMind approach, where you say games are the structure that we need to understand quantum problems, how to turn them into structured problems that AIs can solve. And this is a thing that researchers will have to do. This is where we need capital for building such a research institute. You mentioned sovereignty for policymakers, right? If they get intuition for quantum, that really helps them, and which you can also do with games. 40% of people globally play games, right? And doing, Candy Crush on your phone counts. I once had people say, I'm not a gamer, I just play on my Switch, right? But okay, then you play games, right? And so investors, I would say, if you look at the companies now, I think they are burning a lot of cash trying, keeping up or waiting for this logical qubit to happen. And I don't want to wait for that, right? I want to bridge that gap with, training the workforce and having other people, enabling them making games, making IP for these creative ideas that come out of those playful explorations, and moving quantum from the lab, which it's now, into the living room, right? Where people can play with it and do that, and have my physical tic-tac-toe board, the wooden one I made, on their coffee table, and grow the quantum economy in this way.
Evert, I think it's really fascinating, the gaming initiative. But if you want to start a company out of it, how would you scale it?
Excellent point. I think that we need to then find a way to go viral with this. I'm already getting requests from different points, like from the municipality and policymakers, who say, hey, these games are interesting for us because we are not quantum experts, but they lower the barrier. We can get into this, and requests for podcasts, etc. Imagine esports, right? We have already, this year now in May will be the third national tournament of tic-tac-toe, right? We will maybe do checkers, quantum checkers also, and there's more games that that are in the pipeline. But now, we do this in the quantum community and people who know about it and are interested about it. But from this experience, especially with a game like tic-tac-toe that we all know, and now I breathe new life into that, if we can find, we make the next quantum Roblox or quantum Fortnite, and we turn this into an esports, right? It's a whole new world and different type of games that I'm sure people will find interesting to explore, to see what it can bring. And so here, I think, that would be the approach, going for making these games a larger global phenomenon, esports, facilitating quantum game tournaments, also of quantum games that other people make. I can see that happening. Yeah.
That would be amazing. And if that happens, I will definitely want to visit and track and watch that. So I hope in 5 years' time that there is the first quantum esport tournament.
I will share with you the recordings, and if you have time in May for the third one, this is fun. We have exactly this setting where I don't play, of course, because I made the game, but we do the narrating, and we set it up like the esports people, right? With commenting on the moves that they're making and interesting moves they make. So it's always a lot of fun.